In this video, we're going to be solving trig equations. We're going to look at it using two different methods. We're going to try and solve equations algebraically, and then we're also going to do it graphically. And sometimes looking at the graph makes it a lot simpler than trying to do it algebraically, but we're going to go ahead and try and do both for each of these problems. Algebraically, basically you can think about isolating a trig function on one side and moving everything else over to the other side. And then you can inverse your trig equations to solve for your variable. And graphically, we could do what we've done before, where we solve functions graphically, where we set the equation equal to 0, meaning we move everything from one side of our equation over to the other so that we can set our equation equal to 0. Then we can look at the graph of that function and we can look at the x-intercepts. So x values that make our output 0 would be on the x-axis. So we'll be looking at x-intercepts to solve our equation. So let's look at a basic one here. What if we had sine of x equals 1? So what angle could we plug into our input here so that the sine value is 1? Or in other words, the y value, or the y coordinate, is 1. Well, we know that the y coordinate is 1 if we have an angle that's 90 degrees, or pi over 2 in radians. So if we just inverse sine both sides here, that'll cancel our sine function and leave us with our input, or x is whatever the inverse sine of 1 is. Now be careful here, when we are solving equations using an inverse, we no longer have to think about the domain or the range of an inverse function like we did when we were just evaluating inverse functions. So we're actually going to have multiple answers. So if you think about, take a step back here, if you think about when you solve a square root, like the square root of 9 is just positive 3. However, if you use a square root to solve an equation, you get multiple answers. You get positive or negative 3 if you had x squared equals 9. So much in the same way, when we use an inverse to solve an equation, we're going to have multiple answers. We're not just stuck within the range of an inverse function. So another way to look about this is to look at the graph. The graph of sine of x is a periodic function that continues as far left as we can imagine and as far right as we can imagine. And so if the output is 1 for our sine function, we can see that that's happening here, it's happening here, it's happening here, it's happening as many times as we allow this graph to exist. And so we have an infinite amount of solutions. So one way to say that is, well, the answer is going to be pi over 2 for every interval of the period of that function. So since our interval for sine, or our period interval for sine, is 2 pi, then for every 2 pi interval being added to pi over 2, for example, if I start here at pi over 2 and I go another rotation, I get to 5 pi over 2. Or if I rotate another 2 pi, I get back to here, but that's 9 pi over 2. So from adding 2 pi to pi over 2, then I get an answer to my solution. I can do that all day long if I wanted to. So the way that we fix that problem is we restrict our domain. So for the most part, whenever you see questions that are asking you to solve an equation using trig, most times you'll also be given some sort of restricted domain saying that we just want to provide answers that are within this domain, or in this case just one full rotation. So we're not rotating multiple times, we're just answering the question for one full rotation. So that makes it a little bit easier. We don't have to worry about adding this interval for every part of our answer here. So let's do one where we have a restricted domain. So to do it graphically, since our equation is already set equal to 0, well, we can just type that function in, and we can input our restricted domain. If I do it without a restricted domain, here we see infinite solutions to our equation here. Anytime we have an x-intercept, that's going to be a solution. We're going to go ahead and restrict the domain. So now we're just looking at x-intercepts that happen within this domain. So here we have an x-intercept at pi over 6. There's one solution. And another x-intercept here at 5 pi over 6. So there are two solutions to this equation. Let's see how we could do it algebraically. If we add 1 to both sides, then we have 2 times the sine of x equals 1. We're going to divide by this multiplier out here in front. We're going to divide both sides by 2. So now we have our trig function isolated with everything else on the right side. So sine of x equals 1/2. So what angle is going to give us a sine value of 1/2? Or in other words, what angle is going to give us a y-coordinate of 1/2? So you could algebraically inverse sine both sides to get to that. Or you could think about it using our xy axis here. We're looking for an angle that gives us a y value of 1/2. We know that the coordinate pairs for pi over 6, that angle is going to give us a y value of 1/2. And if we stay up above the x-axis, we know there's another angle that's going to give us the exact same thing in quadrant 2, where the y values are still positive. So this angle 5/6 pi, or 5 pi over 6, also has a coordinate pair that has a y coordinate of 1/2. So there we see our two solutions. We have pi over 6 and 5 pi over 6. All right, let's do another one. Again, we're going to do it graphically and we're going to do it algebraically. Again, because it's set up already equal to 0, the easiest thing to do would just be use a graphing utility. Desmos definitely makes this easier than your graphing calculator. Again, if I plug in my function and the restricted domain, then I can see my x-intercepts. There's only 2 of them that happen on this domain interval here. We have pi over 6 and we have 7 pi over 6. So those are the answers to our equation. But let's make sure we can do it algebraically as well and verify those answers. Let's add 1 to both sides in our equation. And then to get tangent by itself, we're going to divide by this multiplier of the square root of 3. So let's divide both sides by the square root of 3. Now we have tangent of x equals 1 over the square root of 3. Tangent ratios are a little tricky to recognize and remember what angles correspond with them. But to get this ratio, what you end up having to do is 1/2 divided by the square root of 3 over 2. Our tangent ratio is our y-coordinate divided by our x-coordinate. So if I have a y-coordinate of 1/2 and an x-coordinate of the square root of 3 over 2, I know that corresponds with an angle equal to pi over 6. And then we know that we are on this domain interval of 1 rotation, so this is going to happen again, where we also have a positive tangent value. We have positive tangent values in the first quadrant and in the third quadrant. And if I take that coordinate pair in the third quadrant, I just give my coordinates negative values. And then I know that if I divide the y-coordinate by the x-coordinate, I'm still going to get this positive ratio. Well, that coordinate corresponds with 7 pi over 6. And there are 2 solutions. All right, here's another one. Slightly different in that we are going to be combining some like terms when we move things around algebraically, otherwise pretty much the same steps as what we did before. If I take this negative sine of x and move it over, I'm going to add it to both sides. So if I have sine of x plus another sine of x, that means I have 2 sine of x's. Plus the square root of 2. So now we have it set equal to 0. We've moved everything over to the other side. I can take this part of my equation, represent that as a function in a graphing utility. I can graph it and include that restricted domain. And then I could look for my x-intercepts, which are going to be the solutions. So I can see I have an x-intercept here at 5 pi over 4 and here at 7 pi over 4. So those x-intercepts are going to be the solutions. Using the graphing method, let's make sure we can do it algebraically as well. So going back to the step where we left off. If in, well, yeah, I still want to combine my like terms, so that's okay to do that step. Now I'm going to subtract the square root of 2 because I'm trying to get my sine function isolated or by itself. Now I have 2 times the sine of x equals negative square root of 2. So I'm going to divide by 2 to get rid of that multiplier there. Now I have the sine of x equals negative square root of 2 over 2. That's going to correspond with a y-coordinate for one of my angles. So what angle is going to give me a y-coordinate or a sine value of negative square root of 2 over 2? We know the square root of 2 over 2 corresponds with our 45-degree intervals, or pi over 4. But we want it to be negative. We want a negative y value. That means we're going to be talking about quadrants 3 and 4, where we have negative y values. So our pi over 4 intervals that occur in those quadrants are 5 pi over 4 in the third quadrant and 7 pi over 4 in the fourth quadrant. And those were the answers that we already said using our graphing method. Those are where we have y values or sine values that are negative square root of 2 over 2. Alright, so getting a little bit more complicated in these last couple examples, although still using methods that you know how to use, just in terms of trig functions, it's a little bit different. This time we're going to be using a square root to solve, because we have a trig function that is squared, so much like a quadratic, we're going to use a square root to solve it. As it is right now, it's already set up to use our graphing method. It's set equal to 0, so we can go ahead and graph that. Still on our restricted domain of 1 rotation. And we're looking for those x-intercepts. Notice that we kind of have more solutions than we've seen so far. We got 4 solutions this time. We got pi over 6, 5 pi over 6, 7 pi over 6, and 11 pi over 6. All x-intercepts, so those are all going to be solutions to our equation. So let's see why, algebraically, we have 4 solutions this time. If we add 1 to both sides of our equation, trying to get tangent squared by itself here, then we have 3 times the tangent squared of x equals 1/3. Sorry, just 1. We're going to divide by 3 in this next step to get 1/3. Now we have tangent squared of x equals 1/3. So we just want tangent. So to undo a square, we're going to use a square root. We're going to square root both sides. That's going to leave tangent of x on the left side. Anytime we use a square root to solve, we're going to have a positive and a negative solution. So make sure that you include that. We're going to square root 1/3 here. So if we square root a fraction, we square root the numerator and the denominator. So the square root of 1 on top is just 1. The square root of 3 is the square root of 3. We can't simplify that. So our equation is equal to the positive version of 1 over the square root of 3. And it's equal to the negative version or negative 1 over the square root of 3. So we have to solve both of these versions of our equation. That's why we're going to get some extra solutions here. So if we do the positive version here, well, luckily we've already done this problem, so we can refer back. Tangent of x equals 1 over the square root of 3. Back here we found those solutions. Right here to be pi over 6 and 7 pi over 6. So there's 2 of our solutions. If we want the negative version, what angle is going to give us negative 1 over the square root of 3 as a ratio? Well, to get a negative tangent value, we know that that occurs in the second quadrant and the fourth quadrant. Sorry, my notes got cut off a little bit there on my scanning. But this ratio, negative 1 over the square root of 3, in the second quadrant, that's going to have a negative x value and a positive y value. So if I have a y value of the square root of 3, a y value of 1/2, and an x value of negative square root of 3 over 2, that corresponds with the angle over here that's equal to 5 pi over 6. That gives me that coordinate pair. In the fourth quadrant, I'm going to have a negative y value. It's going to be negative 1/2. My x value is positive square root of 3 over 2. And those coordinates correspond with 11 pi over 6 in the fourth quadrant. So there we got 4 solutions. All right, last example. What happens when we use factoring to solve a trig equation? Here's what happens. Let's do both methods again. Let's set everything equal to 0. So let's move this 2 times the cotangent of x over to the left side. So now we have negative 2 cotangent of x plus what we already had on the left side there, cotangent of x times cosine squared of x. Now that it's set equal to 0, we can plug this into our graphing utility. On Desmos, it's going to ask you to be a little bit more specific. When you're multiplying your trig functions, it asks you to put those in parentheses rather than just putting them next to each other. It doesn't like that. Again, if we add that restricted domain, then it should give us our graph that looks like this. We only have 2 solutions. We have it occurring at pi over 2, that's an x-intercept, and 3 pi over 2. So we know those are the solutions that we're supposed to get. Let's see if we can get them algebraically though. Notice here on the left side we have 2 different terms, each with cotangent. So let's factor the cotangent of x out of those 2 terms. That'll leave behind negative 2 in that first term and cosine squared of x in the second term. So now if we look at these 2 things separate, because if this side is going to equal 0 and I'm multiplying these 2 things, well, only one of them has to equal 0 for the entire thing to equal 0. If cotangent of x equaled 0 and I multiplied it by this, the whole thing would be 0. Or if what was in parentheses was equal to 0, then this times that would also be 0. So what you need to do is just set each of these separately equal to 0. And we can find our solutions. In doing this, sometimes you get one of these to have no solution, and that's okay. As long as we find a solution for one of these, we'll be okay. So cotangent of x has to equal 0. So what angle measure is going to give me a cotangent ratio that's equal to 0? Well, for tangent, I'm comparing y to x. So cotangent, I'm comparing x coordinates to y coordinates. So as long as the x coordinate is 0, then my ratio will all be 0. That occurs at 2 spots, either at pi over 2 or at 3 pi over 2. So those are our 2 solutions that we have for here. Either one of those is going to give me a cotangent that's equal to 0, which is going to make my whole equation equal to 0. Let's see if we have any solutions for what's in our parentheses. I'm just going to rewrite it so that I have cosine squared of x minus 2 instead of it written in this way. Doesn't matter. If I add 2 to both sides and get cosine squared of x by itself, and then use a square root to get cosine of x, then cosine of x is going to be equal to positive or negative square root of 2. Well, if we graph that and see if we can find a value on our cosine graph that's equal to the square root of 2, here's our cosine graph. Notice that our range, possible answers or outputs, don't go past 1 or negative 1. If I back up and instead graph what I had right here and look for my x-intercepts, do I have any x-intercepts here? We'll notice that when I graph it, my graph doesn't even cross the x-axis, so I can't have any x-intercepts. So there's another reason why I don't have any way to find a solution where the cosine of x is going to be either positive square root of 2 or negative square root of 2. It's outside the range of this function. I don't have any solution to this part of the equation. And that's okay because we already found 2 solutions that work, so we'll go ahead and just list those. All right, so there's a lot of ways that we can solve trig equations algebraically. However, always rely on that graphing method if you're ever stuck algebraically. That's going to be your skeleton key. You can always, I hope, move things around algebraically and set the equation equal to 0 and then just graph and find your x-intercepts. However, it's always good to be able to do things graphically and algebraically, so make sure you practice both. And as always, email me if you got any questions about this.